Hello, everybody. Welcome back to Learning as a Hobby. In this video, I want to finish up section 1.7 in the Taylor book, Classical Mechanics. This will be the end of chapter 1 in that textbook. So we're going to do the solutions to the problems at the end of the section in this video. So let me bring up my answers. All right, here we go. Okay, let me just move this out of the way. Okay. So we'll go through them. There's a couple questions I left out because they involve you need a computer to computer algebra system to do them, and I don't have access to that. Or you could use Python, but I don't know how to program in Python, at least not yet. That's something I'm going to have to learn how to do at some point in the future. So I skipped those problems, but I did the rest of them here. So section 1.7, question 1.41 is the first one in that section. If you recall, it's been a week or so since I posted these chapter notes on that. This section was about Newton's second law in polar coordinates. All right, so let's see. 1.41 says an astronaut in gravity-free space is twirling a mass m on the end of a string of length r in a circle with constant velocity omega. Write down Newton's second law in polar coordinates and find the tension in the string. All right, so here's the solution. So you're swinging the mass or whatever it is on the end of your string. The string has length r, so that's fixed. So the radius of the circle is capital R, and also it has fixed angular velocity of omega. Okay, so phi dot is equal to omega. All right, and then just setting up Newton's second law. So the force Fr r hat plus F phi hat is equal to m r double dot minus r phi dot squared r hat plus et cetera. We derive this formula in the chapter section. But now here, anything that has a derivative of r goes to 0 because the radius of the circle is fixed. So when you simplify everything, we just end up with this expression here. This one over here. Okay. So notice that you only the term in the radial direction survives. So this should be equal to this expression over here, right? And this should be 0. Okay, so that means that the force in the radial direction is negative m capital R omega squared, just, replacing little r with capital R and replacing phi dot with omega, right? Because that's the angular velocity, right? So you get negative m r omega squared. That's the force in the radial direction, which is the negative of the tension. The tension in the string goes this way, and the force is going that way. Okay, so that means that the tension has to be equal to the expression that I have up here. Right, so the tension is mr omega squared. And that's essentially the answer to that problem. Right, go on to the next one. Prove that the transformations, got to move this a little bit further up. Prove that the transformations from rectangular to polar coordinates and vice versa are given by the 4 equations that we did we talked about this in the chapter itself. Explain why the equations for phi are not quite complete and give a complete version. Right, so here the formulas that go from polar to Cartesian coordinates are just a consequence of the way that we define the trig functions. So if you remember your trigonometry, so here cosine of phi, right, this is the angle phi over here, and this is the radius of the circle r. Then cosine of phi is equal to x over r. And then you can just solve for x by multiplying both sides by r, and you get this formula here. So x is r cosine phi, and similar thing for sine. Sine is defined as y over r, therefore y has to be r sine phi. So it's just a consequence of direct consequence of the way that we define the trig functions. Right. And then for going the other way from Cartesian coordinates to polar, it's slightly more complicated, and because of the fact that polar coordinates are not unique, polar representations of geometric points are not unique. So we get this formula here just by looking at the circle that we have above, right? The radius by Pythagoras is given by x squared plus y squared square root. It's a little bit better, I think, to write this in terms of r squared, because you can have a positive, you're allowed to have positive and negative radii in polar coordinates. So I actually prefer to write it like this, because that includes the negative as well as the positive version for r that you can pick. You know, if you choose the negative version for r, you just have to adjust theta accordingly. And then most of the problems come in with the angle. So if you look at the circle here, by the definition of tangent, that's equal to y over x. So tangent of phi should be equal to y over x. You can take the arctan of both sides, and that solves for phi. So phi is arctan of y over x. But that only works if x is positive, right? Only if you're in quadrant 1 or quadrant 4, where you know, the angle is measured in the negative acute sense. So we'd like a way to extend the formula to quadrant 2 and quadrant 3. In other words, when x is negative. What you do then is you just add or subtract the period of tangent from the angle, and that'll get, if it's in quadrant 4, you add pi, that'll bring you to quadrant 2. Same thing if you subtract pi, that'll be in quadrant 2. Or if it's in quadrant 1 phi, then you can add pi, that'll bring you to quadrant 3, or subtract pi and they'll bring you to quadrant 3 as well. So but just this is sort of like not as nice a way of representing it as just leaving it as tangent phi equals y over x. So these are the versions that I prefer to use, and that I think many people probably do, just because of that issue with the angles and the radii. So that's essentially the answer to that question. Right, next one, 1.43. Prove that the unit vector r of two-dimensional polar coordinates is equal to r equals x hat cosine phi plus y hat sine phi, and find a corresponding expression for phi hat. There's actually, I think, 3 parts to this, so let's actually do them one at a time. So let me show you the answer for part A. Right, here's the answer for part A. So just by, again, trigonometry, if you look at the position vector here, r hat, the x coordinate is equal to, so this is this has unit length because it's a unit vector, so the radius is 1. So r hat is equal to x r cosine theta, but r is 1, so that's the same thing as x hat cosine, sorry, did I say theta? I meant phi. That's the same thing as x hat cosine phi. And similar thing for the y coordinate, it's y hat r sine phi. But again, r is equal to 1, so you get y hat sine phi. Right, so that shows that r hat is equal to that that expression in terms of Cartesian coordinates. Okay, and then to find phi hat, we just use the fact that phi hat is orthogonal to the unit vector r hat, and it always points in the positive direction that phi would increase. So phi hat would be equal to x hat cosine phi plus pi over 2, right? Because you're rotating by an angle of pi over 2, plus y hat sine phi plus pi over 2. And then you just use the sum formulas for cosine and for sine. So cosine phi plus pi over 2 is cosine phi cosine pi over 2 minus sine phi sine pi over 2, which simplifies to just minus sine phi, because sine of pi over 2 is 1 and cosine of pi over 2 is 0. And oh, I just realized this should have a hat on top. This should be an x hat here. Okay. And then same idea for the y coordinate. Sine phi plus pi over 2 is sine phi cosine pi over 2 plus sine pi over 2 cosine phi, which simplifies to cosine of phi, again, because cosine of pi over 2 is 0 and sine of pi over 2 is 1. All right, so that gives you the expression for oops, for phi hat. All right, let's look at part B. B says, assuming that phi depends on the time t, differentiate your answers in part A to give an alternative proof of the results 1.42 and 1.46 for the time derivative of r hat and phi hat. So let's see, I did that down here. So you just differentiate with respect to time. Don't forget that phi is a function of time, so you need the extra factor of d phi dt, right, by implicit differentiation. All right, so when you do the derivative, you get what you want. You get phi dot phi hat, and that's the value of dr hat dt, and same thing for d phi hat, d phi hat dt. You just differentiate, and remember your implicit differentiation, and that gives you the expression that we derived in the chapter. Right? It says just another way of deriving those formulas for the derivatives of the unit polar unit vectors. All right, 144, verify by direct substitution that the function phi of t is a sine omega t plus b cosine omega t of 1.56 is a solution of the second order differential equation 1.55, which is this differential equation here. Oh, I just realized something. This should be, so this should not be a hat on top. This should be a double dot. Should be a double dot on top over here. Okay, so that's a second order ordinary homogeneous linear differential equation. Right, so just take the derivatives and show that it satisfies the equation. So take the first derivative, you get a omega cosine omega t minus b omega cosine omega t. Those extra omegas come from the chain rule. Right, and then take the derivative again, you get negative omega squared a sine omega t minus omega squared b sine omega t. You can factor out the negative omega squared and notice that you get negative omega squared times omega. I keep saying omega, sorry, I mean phi. So you get negative omega squared times phi. All right, and that shows that it satisfies the differential equation. And that's essentially it. Since it has two arbitrary constants, this is the general solution. All right, next one, prove that if v of t is any vector that depends on time, but which has constant magnitude, then the time derivative of v is orthogonal to v itself. Prove the converse, that if the time derivative of v, excuse me, is orthogonal to v itself, then the magnitude of v is constant. And then he just says this is a very this is a very this is a very handy result. It explains why in two-dimensional polar coordinates dr dt has to be in the direction of phi hat and vice versa. It also shows that the speed of a charged particle in a magnetic field is constant since the acceleration is perpendicular to the velocity. This is just a note that he has underneath the question. So again, this is relatively straightforward. So start by letting v, the magnitude of v be constant. Then we can use a fact about the dot product. The length squared of the vector v is equal to the dot product of v with itself. If you differentiate that, you get this expression here by using the product rule. That's equal to 0, so that shows that part. So in other words, v and dv dt are orthogonal. Remember, if their dot product, if two vectors dot products are 0, they're orthogonal. It's the definition. And then we can go the other way around. If the two vectors are orthogonal, then their dot product is 0, which you can go backwards in the derivation above. And that shows that dt of the length squared of v is 0, which means that the length squared has to be constant, which means that the length has to be constant. And that's basically it. Right. Next one. 147, let the position of a point P in 3 dimensions be given by the vector R, which has Cartesian coordinates x, y, z, and rectangular coordinates. The same position can be specified by cylindrical polar coordinates rho, phi, z, which are defined as follows. Let P prime be the projection of P onto the xy plane, while I think there should be rho. Sorry, rho should be the projection. I think that's just a typo. There should be rho. While z is the third Cartesian coordinate unchanged. Right, so part A, make a sketch to illustrate the three cylindrical coordinates. This one has several parts too. We'll take them one at a time. Make a sketch to illustrate the three cylindrical coordinates. Give expressions for rho, phi, z in terms of the Cartesian coordinates x, y, z. Explain in words what rho is. All right, let's do that one first, and then we'll look at the other parts. I think there's 3 parts or 4 parts, 3 parts. All right, so here's the picture. This is the position vector here. It has coordinates x, y, z, or rho, phi, z uh, in cylindrical polar coordinates, as he calls it. All right. So rho is the distance from the vertical axis, the z-axis. Phi is the angle that, or if you want to think of it, it's the polar angle. It's same as the polar angle in polar coordinates. And z is just the height of the point. Z is the same in both Cartesian and in cylindrical polar coordinates, right? So we get this expression here: rho squared is x squared plus y squared. Tan phi is y over x, and z is just the same z coordinate. Okay, and what is rho? It's the horizontal distance from the z-axis, like we said. Right, so that answers part A. And then in part B, I think they wanted us to write down the coordinates of r, the position vector, with respect to the new coordinate system, the cylindrical polar coordinates, which I have written down here. So r is equal to rho hat plus z hat. I haven't really talked about the unit vectors there, but you can see them I have them drawn here in green. This is the unit vector in the rho direction. This is the unit vector in the phi direction. These make a 90-degree angle. And this is the unit vector in the z direction. All right. So in terms of those coordinates, that gives you the position vector r in terms of those unit vectors. Right. Let me just erase this. And let me see. Let me go back up. So describe the 3 unit vectors. Rho phi z, sorry, rho hat phi hat z hat, and write the expression of the position vector in terms of these unit vectors. So that's what we just did. And then the last part of this question is this one, part C. Differentiate your last answer twice to find the cylindrical components of the acceleration of the particle. To do this, you'll need to know the time derivative of rho hat and phi hat. You could get these from the corresponding 2-dimensional results. He means in the chapter when we talked about polar coordinates, or you could derive them directly as in problem 148. So here's my derivation. So the derivative of rho hat dt is equal to, did I not? I think I just used them like he said. I thought I derived them, but I guess I didn't. Anyway, d phi hat dt is equal to phi dot phi hat, because it's just the polar radius, right? And we know that the derivative of the polar radius is that quantity. D phi hat dt is negative phi hat rho hat, again, for the same reason that it is for polar coordinates. And the derivative of z hat with respect to time is 0 because it's constant with respect to time, right? And then we can differentiate the position vector now to find the first derivative and then the second derivative to get the acceleration. And it's essentially identical to the derivation for the polar coordinates, with the exception that when you differentiate z, you get this extra factor of z double dot z hat. Right? And when you do that, if you look, the expression is almost identical to the expression for polar coordinates, with the, like I said, the exception that you get this extra component in the z direction. Okay. All right, 1.48, find expressions for the unit vectors rho hat, phi hat, z hat of cylindrical polar coordinates in terms of Cartesian coordinates, x hat, y hat, z hat. Differentiate these expressions with respect to time to find their derivatives. So here he just wants us to do it another way, which I'm doing here. Again, from what we know about polar coordinates, rho hat is x hat cosine phi plus y hat sine phi. If you differentiate that, you get phi dot phi hat. I won't go through the details here. It's almost identical to one of the other problems that we just did. So phi hat is negative sine phi x hat plus cosine phi y hat. And if you take the derivative, you get negative phi hat rho hat. And then, of course, z hat is equal to z hat. So that's it. The derivative of z hat is 0 because it's constant with time, right? So actually, maybe I should write that down here. dz hat dt is 0. Right. I think this is the last problem in the section that I did. Imagine two concentric cylinders centered on the vertical z-axis with radii r plus or minus epsilon, where epsilon is very small. A small frictionless puck of thickness 2 epsilon is inserted between the two cylinders so that it can be considered a point mass that can move freely at a fixed distance from the vertical axis. If we use cylindrical coordinates rho phi z for its position, problem 147, he's just saying, the derivations that we just made. Then rho is fixed at rho equals r, while phi and z can vary at will. Write down and solve Newton's second law for the general motion of the puck, including the effects of gravity, and describe the puck's motion. So he's a little bit unclear, but I think I'm interpreting what he's saying is that the z, the negative z direction is, I guess, down. It's where, that's the direction that gravity is accelerating downward. I'm making an assumption there because he doesn't say in the problem, but I'm assuming that's what he means. So we have the acceleration due to gravity on the puck. Let's say that the puck is over here. It's being accelerated down this way with magnitude negative mz z hat. Okay. So this is our puck. All right. So there's so rho is fixed, right? The radius of where the puck is situated will always be constant. It's because it's stuck between those two cylinders. So it has radius r. So rho will be constant at r. And you have the acceleration due to gravity going downward. That would be the force in the z direction. So negative mg is mz double dot by Newton's second law. You also have two normal forces. There's one normal force going this way. I call that Ni. This would be in terms of rho hat. And that's due to the inner wall here of the can or whatever. And then you also have another normal force pointing this way. That's from the outer the outer side of the can pushing inward. The net force, the net normal force on the puck then would be Ni minus N0. So here I'm just writing it as N. Right. So the force in the rho direction is the normal force N, that the net normal force N, which by Newton's second law is equal to m rho double dot minus rho phi dot squared, which when you simplify all of that, remember rho double dot goes to 0 because rho is fixed it's a fixed constant, right? So that simplifies to negative m capital R phi dot squared. Okay, what that tells us is that, whoops. Notice that over here, m is a positive quantity, r is a positive quantity, and phi dot squared is greater than or equal to 0, right? It's non-negative. So that means that the value of n here has to be less than or equal to 0. Okay. All right, and then the force in the phi direction is 0. There's nothing accelerating. There's no force acting on the puck in the phi direction. So that would be 0. And again, by Newton's second law, that's equal to this expression here. And again, rho dot is 0 because rho is fixed. And when you plug in capital R in for rho, you get this expression here. So mr phi double dot is equal to 0. So now we have our differential equations that we have to solve, which I did on the next page. Right. So from the first equation, negative mr phi dot squared equals n. That implies that f rho hat points inwards towards the center of the cylinder. That should be hopefully clear because again, the motion is circular, right? So the acceleration is towards the center. So it's accelerated towards the center. And also from that, we get that the what's it called? The frequency is equal to some constant omega. So phi dot is plus or minus the square root of negative n mr. That just comes from solving this for phi dot. Okay. And so I'm going to call that omega. All right, phi double dot is 0 from that second differential equation. You just divide by m and r. Just to remind you over here. I can divide out by mr, and that gives me phi double dot equals 0. Right, so that means that phi dot is constant, which is equal to the initial frequency, which is omega, and then you integrate that one more time, you get omega t plus phi 0, which is the initial angle that the puck is starting at. Right, so that's a linear function, and z double dot equals negative g. Again, you can divide out by the mass because it's a factor on both sides. Integrate that with respect to time, you get z dot is negative gt plus z dot 0. In other words, the initial velocity in the 0 in the z direction. Right. Integrate one more time, you get negative g over 2t squared plus z 0 dot t plus z 0. Just so it's not confusing, this is initial velocity in the z direction, and this is initial position in the z direction. Right. So you get a quadratic function in the z direction. So you know it's the usual the usual it's just being accelerated by gravity, so it's in free fall, right, in the z direction. Right. Therefore, the motion of the puck looks like this. Right, which gives us, if you actually draw that out, it gives you the shape of a helix traced in the downward direction. So it's going to look something like, something like that. With I didn't draw it very well. The radius should be the same, but kind of looks like a spring if you want to think of it like that. Something like that. Right. And that's it. I think that's the last problem from this section. Just erase this stuff here. Yeah, I think that's the last problem in the section. So let me stop the screen share. All right, so that's the end of chapter 1 in the Taylor book. So I'm going to move on to something else for a little bit, and then we'll, hopefully get to chapter 2, start on chapter 2 pretty soon. I want to start moving forward in the physics stuff because I feel like I've been haven't had so much time to work on things lately, which is, I don't really have any control of that. It's due to work and stuff like that. And actually, I haven't been feeling that great. You can probably hear it in my voice. So I'll see you guys in the next video. It'll probably be the solutions to chapter 4 in Spivak. Remember, I still have to get through the 3 appendices in chapter 4 as well there. So we're still going to be on chapter 4 in Spivak for a little bit. I'm looking forward to getting to chapter 5 because that's where the calculus stuff starts. Chapter 5 is on limits of functions, so hopefully we'll get to that pretty soon. And then I still have to get to the all the other stuff. I want to finish chapter 1 in the differential equations book too, so I might make a bit of a push to finish that as well. And then we have Schifrin and Agsler as well. So I've been falling a little bit behind, but I'm going to try and catch up a little bit. So thanks for watching, everybody. If you like this video and you like this type of content, please do like and subscribe to the channel because it helps the channel grow. It helps other people. YouTube, suggest the videos to other people that have the same interests as you and I, and it helps everything keep moving forward. So I'll see you guys in the next video. Until then, keep learning, everyone, and I'll see you in a little while.